Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about a very important overlooked topic, that is round trip efficiency, or RTE. So let's dive deep into it. So what does this mean? Well, this is a core vector of energy storage or energy carrier. They both have to basically go through this, aka battery or hydrogen, does not matter. Now, what does that mean to you and me? Well, it simply means basically how much kilowatt hour or unit of electricity we put in versus how much you can get out of it. For example, you paid 100 unit of electricity here to get 100 units into your cable, and that cable charges your battery. Battery has charger, battery has its own internal resistance, all that jazz. How much energy your wheel has? Basically, if it's a very cheap, very poorly built, if you took 100, you should get 80. But if it's a well-built system, you could easily look at 91, maybe 93. So of course you would want to, because again you are paying for it, you would want to go extra mile based on the same amount of energy. So efficiency matters. How do we calculate that? Round trip efficiency, because you are paying at the point of charging. So round trip efficiency, and you have to pay for all the wasted energy also. So it's not like, okay, my car is wasting it, who cares? No, it matters because you are paying for it. So if it's a big system, let's say a bus or a truck, and you are charging a lot and it's wasting like 10% every time, that will pile up very quickly. Like before you realize it, will like, dude, why the heck it's costing me so much? Because it's not efficient. You have to pay for it. So, and bigger the basically inefficiency, higher the penalty. So you must make a system that is efficient, as in round trip efficiency. So you have to pay for it. Everybody hates the idea of paying for it, and waste heat also becomes an issue to deal with. For example, a system that is only 80% efficient means has 20% of waste heat production, versus a system that could be very efficient, let's say almost 94%, that only has 6% of total energy as a waste heat, meaning your radiator would be far more relaxed, your coolant system will be far more relaxed, overheating would be far less of a challenge. So for that reason, you have double YME. So for many times, people will, like, if they are making a cheap car, they will be like, go into the chemistry that is like, in terms of round trip efficiency. So you will put 10 kilowatt hour, you will only get 6 kilowatt into your motor, 6 unit into your motors. That's 60% efficient. Sloppy at best, useless at worst. So again, not a big issue for very cheap basically three-wheelers and all that jazz. But again, you can see like you're wasting 4. It is an issue. And compare that to, let's say, a quality, well-manufactured vehicle, you could have 10 unit of energy going in, almost 9.8 going into the traction motor. So that's what we want. That's what we are working towards, because again, that also means the waste heat production on that vehicle is far less, and the amount of money the person has to pay is also less, even though the capital cost of that battery pack would be higher. So it does matter. Everything has to go through this, and we have to understand this. And again, this is the battery's normal understanding. So you have state of charge, basically how much charge it has, and then you have depth of discharge. Most BMS will not allow you to drain the battery to 0%, and again, most battery will be bricked if you allow it to drain to 0%. So generally there is a cap cut off at, like, let's say 5% or 10% or 15%. There would be a cap of cutoff point, and BMS will not allow you to go below that. And then you have round trip efficiency that directly affects the internal resistance of the cell, basically how much energy you are wasting when you are putting in energy, and how much energy you are wasting while you are pulling out. Yes, in both times it wastes energy. And then you have self-discharge rate. Now generally batteries are good enough where self-discharge rate is not a very big issue, but it is an issue if you left it. Basically compare this to a diesel vehicle, because diesel does not go bad as quickly as compared to petrol. Petrol gets bad very quickly. If you have a diesel engine, that is a big robust engine, it's gonna last, like, you can have start it again after 1 or 2 years, hand crank it maybe, or have a different battery, but it would work. Battery would be completely discharged. So this is what we are talking about here, a vector that we must understand in order to understand where we are wasting money and where we are dealing with wasted heat. People hate paying for money. So where these losses are coming from? Well, first you have to understand there is a law in the universe that is known as thou shall not have 100%. No matter what you do, no matter who is your engineer, no matter what tech genius you have, you will not reach 100%. Anybody is claiming 100%, run away. Unless it's talking about heat pump, at that point it's still not 100%, but it's just pulling heat from somewhere else. So it's like, okay, 400%. So 100% you cannot have. 100% round trip efficiency is just like, no. At best case scenario, it's almost like a heating element if you want to use. You may reach that, but even then it will be like, unlikely. So what is the biggest loss? Well, there are certain laws. One of the big daddy laws is thermodynamics. It's the second law of thermodynamics, and that puppy loses most amount of energy. And then you have electrical resistance, or what we call Joule heating, meaning you are not dealing with superconductor. Be it supercapacitor, be it batteries, they have internal resistance. The electrons just not like lol. They have to actually travel through the resistance, meaning they do waste some amount of heat. So engineers do work their ass off to reduce that loss by reducing the internal resistance. And then you have a different layer, that is chemical layer, electrochemical losses, meaning every time when you are like, hey, I'm going to take the lithium ions and force it through something, it's going to take some energy, and is there going to be certain loss that is on the chemical level. You cannot bypass this. You have to waste that energy. Same will go with sodium, same will go with lead acid. No matter what, there will be certain losses. Now again, some chemistry would be really bad, for example lead acid battery. Some chemistry could be really good, like lithium. And again, if you are dealing with some mechanical system, well, then you will have mechanical friction and wear and tear, so that will also have some penalty. So, and there are many more laws. If you are dealing with photons, like how much solar panel, there is a law regarding that, how much useful energy you can get out of a solar panel. So there are many, if you can think about it, I can guarantee you there is somebody who has already figured it out, and there is a law for it. So there are a lot of laws, and that's why under known circumstances, no matter what you do, you cannot reach 100% forever. Like that's like, no, you can try 99.99999, but you will never reach 100. So that's there. And another aspect, this is very crucial, you must understand this. Many times people trick you at this stage, is that not all law have same penalty. For example, the worst offender is thermodynamics. Basically, if you are going through chemical route, or let's say heat engine route, run away. You're going to waste most of the energy just in that conversion phase. So thermodynamic and chemical losses are the worst, like the worst option we have, and most taxing. What does that mean? Like, that simply means if you're dumping 100 unit of energy, you'd be wasting flat out at super optimum system 55% of it, at realistically 70% of it, meaning only 30 unit of energy would be available for use, even though you charged for 100. So that is the whole point you must understand. While other losses are losses and they do cause issues, compared to thermodynamics, they are chump change. So, and electrochemical losses are much more moderate. So whenever you are going through the thermodynamics routes of hydrogen system, basically dumping direct current into basically a beaker and taking water with H2SO4, basically water plus electrolyte, you want to split it up. That process is a thermodynamic process. You are losing a lot of energy. And again, when you are trying to undo it, Control Z it, or basically get energy out of it, that will also waste a lot of energy. These two steps will waste so much energy, you will be shocked. Basically, if you dumped 100 unit while charging it, you're not gonna get more than 30, 35, maybe while you're draining it. So that's the penalty. Compare that to battery. So you have an empty battery, you start charging it, there will be heat. Again, you will have waste heat. Where that heat is coming from? It's coming from internal resistance of the cells. You must have known, like all battery, how much oomph they can deliver is limited by internal resistance. That's there. Now again, that's why we want to do tabless geometry and all that jazz to make sure the internal resistance is as low as possible. The heating would be as low as possible. So that internal resistance is there in series when you are charging it. That was wasting some amount of energy. It's fully charged. That's the stored amount. You will have some amount of self-discharge, but again, for short duration, let's say a week or so, it should not matter. And then you have, while you're draining it, basically driving the vehicle, you still have waste heat coming out of the battery box itself, because again, that internal resistance means it's creating far more oomph, and that will be your wastage. And then you will have delivered energy. Quite efficient. This not efficient, this very efficient. And be mindful, just because that has losses does not mean it's the same losses as this. Just because you have so many layers and so many laws does not mean all laws have same penalty. The worst penalty is for thermodynamic. Basically, thou shall try to avoid thermodynamic pathways if possible. Otherwise, you will waste so much of it, it won't even be funny. Now we come to energy storage systems. So the best option you have, basically, if you are so sensitive, basically like I need something good, supercapacitor is your best puppy. Basically, this puppy can almost like basic supercapacitor that you can just buy. And again, I'm not talking like quality systems that are used for fancy things. Just buy, it will be almost 95% efficient. Meaning, if you dump 100 unit into it, you should be able to get 95 without issue. And the quality one, like top quality ones, those can easily dump 98 units out. So it is very efficient. Why? It's just electrostatic energy, so to say. energy goes there, not electrostatic, electrodynamic. Again, engineers can comment it down. Basically, there is a field that is storing the energy. Now, what about the other losses that it has? Well, that losses is coming from the conductors, because again, it does have resistance, very low resistance, but does have resistance. It will waste some percentage, and some other parts are there. The worst offender on those puppies are self-discharge. That's why nobody likes to use them. Basically, you dumped 100 unit into this, you can use 100 unit like 5 seconds later. Awesome. But if you waited like one day, yeah, most will be gone. So self-discharge rate is very brutal and very bad. Although for short duration, it is super awesome because it only has ohmic losses and the penalty is almost negligible. Like, you don't have to worry too much about it. Now, what about lithium ion batteries? Well, again, they are significant upgrade from lead acid batteries. But when they started, basically when 1990s, you have the era of lithium ion patent, and Sony starting to bring out lithium batteries for their handycams and another smart lithium, I think they used to call it. That was 85%. As we became better, efficient, more adept at manufacturing and cell geometry, we pushed that puppy to 95%. So if you have money, you're gonna get 90%. If you have a lot of money, you're gonna get 95% right now. And the primary reason why the losses are higher compared to a capacitor is because it has electrochemical losses plus ohmic losses. And be mindful, resistance are higher in this puppy compared to that. So it's a double whammy. That's why no matter what you do, you will never get it as efficient as this. But there is an overlap. You could have a scenario where you like not great this, ultra great batteries, they could have almost same round trip efficiency, and this will have better basically self-discharge performance. So almost, we are like almost to a point, and that's why you will no longer see people are like, okay, what if we put super capacitor? It's the gap is like so narrow, it's like and again, this does not have high self-discharge rate. So more than enough times, if you have good battery, good cell chemistry, good geometry, good packaging efficiency, you do not need this anymore. Again, that's why this company was sold to Tesla. Tesla bought this and they took the technology of dry system, dry electrode coating, and they are using that for the big cell puppies right now. And again, that's how they also upgraded the cell design to tablet to tabless. So that is there. And what about pumped hydro? That's the biggest battery we have on the planet, gigawatt hour of capacity. So that puppy is like 65% to 85%. So if it's a well-maintained system, you should be in 70s to 80%. 85% is like really, really fine-tuned system. Now, why is that? Well, pumps are not 100% efficient, even compared to the mechanical motion that is on the shaft itself versus how much liquid is traveling up. It's not 100% efficient. And turbine, again, the same thing. Turbine will waste some amount of energy. So those things are there, and then you have mechanical frictions and all that. Like, why would you have friction? Well, bearings reduce friction, do not eliminate it. And on top of that, you have high pressure water. So you have seals there. Those seals are friction points, like very high friction points. So you do lose some amount of energy. So if somebody comes to you, it's like, we're going to have pumped hydro that's going to be like 95% efficient, run. It's a lie. Again, law of physics is like, nah, bro. Nah, bro, no. Like, 80% should be doable. 85, you're pushing it, as in like in terms of cost, but it should be doable. So 80, assume that to be the baseline. So this is just the energy storage context, and that's why these things have such a different characteristics, because again, the laws that are affecting them are different. Then we come to the worst brain damage of humanity, that we call energy carriers. Energy carrier simply means basically you are charging it up. Basically, fossil fuel to us is not an energy carrier, even though technically it's a solar energy carrier. Basically, it's a converted biomass that has been cooked by Earth and we are extracting it. So that point of view, it is a solar energy with extra steps. But again, because we are just extracting it, not making it like a biofuel, so it is like an energy source for us. So hydrogen is an energy carrier. You have to make it, and you generally use it as a gas format. Does not matter pressurized or not, it's a gas format, and it's a great thing. We have to do this, and we have been doing this because it's a feedstock of industry. Meaning, if you look into like when we started to mass produce hydrogen, it's an early industrial revolution. It's like, why? Well, we need it for many things, be it ammonia production, be it steel processing, be it a whole lot of industries. We have to have this. It's like, it will not work. So okay, where we are getting that hydrogen from? We are in steam reforming to methane, CH4. Basically, we are cooking that puppy, breaking it up into carbon dioxide and hydrogen, and that hydrogen we are utilizing. So if people are thinking that, hey, we are running a hydrogen car, is so efficient and all that, no, the carbon dioxide is coming at that steam reforming plant, not at your car. It's just like out of sight, out of mind. You're still producing bonkersly large amount of carbon dioxide. It would be actually more efficient in terms of CO2 production, just use the methane directly. So, but again, we have to figure out a way to make quote unquote green hydrogen, because again, industry do need it as a feedstock. So should we research it? Absolutely. Should we pay money into it? Undeniably so. It's good for country's economy. Using it as a fuel is wasteful. Now be mindful, this is ancient technology. We have known this from 1875, and we had like the early stage of like a high density hydrogen fuel cell at around 1930. Yes, 1930. So flat out, why it's useless as a fuel? Again, let that be very clear. We have long experience with this. It's not like me saying it. It's like history book. Please open it up. So long history is there, and reality is it has low density, because again, people do not study in school. They do not understand that hydrogen is the lightest element, meaning you can't carry the damn thing. So for example, if I'm a salesman and I want to cause you brain damage and destroy your country, I'm going to come to you and I'm going to tell you an absolute truth, that is, hey, hydrogen has 130 megajoule per kilogram. You're like, whoa, I do not understand what does that mean. Here's the deal. Compared to petrol and diesel, you're looking at 22 to 30 maybe. I was like, whoa, that means this puppy has 3 times more power. Is that true? Scientifically, factually, absolutely. It's just that because you did not pay attention in school, you did not realize how the hell you're gonna carry it. Hydrogen does not come in solid form. There is no 1 brick, 1 kilogram of hydrogen. That does not exist. The only way to carry hydrogen logically is liquid hydrogen. We use that in rockets. What about that? Basically, how you carry it. Basically, whenever you're talking about plane are not carrying in kilograms, they are carrying in volume. If you look at the trucks, if your plane is being refueled, you pay attention to it, it will say KL, kiloliters, volume. So how much there? Well, if you compare 1 liter of petrol, diesel or jet fuel versus 1 liter of liquid hydrogen, yeah, that's 8 versus 32. Yeah, hydrogen is too light to be useful. We've been there, we built it, done it. Outcome is the same. It just does not have enough. What does that mean? Well, it simply means when Soviet Union built this, or America built a fighter jet with hydrogen, and they were smoking so much, they were like, hey, what if we build a bomber, high altitude bomber that was using hydrogen? They realized something very mathematical, that 1 liter of liquid hydrogen only has 8. What does that mean? That simply means if your jet engine is 100% efficient, you are only getting 8 megajoule out of it. And again, law of physics is like, brah, no, that's not happening. But let's just assume for the sake of argument. What does that mean? Well, that simply means your normal, basic jet engine can, if it has 25% efficiency, it will exceed 8 megajoule. Meaning modern jet engine is like, bro, hydrogen, even if it is giving you 120%, you can't compete. We crossed that, and they crossed it in 1950. That's why I said we built it, we used it, then we canned it. Hydrogen is not a new cutting edge technology. It's an abandoned technology from 1930s. We built it, we used it, we realized it was stupid, then we let it go. That's why basically space missions used to use hydrogen fuel cell, for example, Apollo mission and space shuttle, and then they abandoned it. Like take Apollo, dicto copy Control C, Control V to basically Artemis missions, basically Orion capsule. Why the heck it has battery? If hydrogen had weight savings, they would have used it, because again, weight is very sensitive in terms of rocket systems. And if it had basically cost is not an issue for rocket systems. Again, battery is just better. Again, round trip efficiency. So, and because of the low density, you can't carry it. So we learned it the hard way. And again, people are like, we are building like Bosch is like, we are coming up with hydrogen injectors and all that. I'm like, bro, we had it. BMW built it, Honda built it, Audi built it, every Tom, Dick and Harry built it. We had it long ago. Like during the oil embargo era, everybody was smoking, and that is the time when people started smoking that 130 megajoule versus 30 megajoule. It's like, bro, that's in kilogram. You do not measure fuel in kilograms, you measure it in liters. Can you carry the damn thing? And then people will smoke more, and they're like, oh, but we are not using liquid hydrogen, we are using gas. And it's like, did you not do anything in school? Solid, liquid, gas. Compressed gas is still lower than liquid. If you are only getting 8 megajoule, no matter what you do when you are compressing the goddamn hydrogen, you are not going to get 8 megajoule. You will always be lower. And let's be hyper optimistic. That only gives you what? 6 megajoule if you are 600 bars, which again, most systems do not have 600 bar. They are only focusing 350 bars because again, tanks become too expensive at that point in time. That probably is 4. That's 4. And again, yeah, that's why that jumbo jet that actually had liquid hydrogen, it had like this whole back section was hydrogen tank. And again, because the European Union is smoking, they're like, we shall ban all hydrocarbon by 2050. And Airbus, again, a European company, they're like, what the hell? And they're like, okay, build a hydrogen system. You look into their Airbus A380 that is hydrogen based. They have 4 ginormous tank to feed a tiny passport engine. That engine name is Passport, used for like private jets and all that. Tiny engine. Why? Because if they feed their giant engine that is actually flying the plane, yeah, it's going to run out like this. Does not have the energy density, like law of physics. And again, thankfully, I have seen almost all pilots, they do understand this, that it cannot fly on hydrogen. We're like, bro, we've been there, done that. We know it does not have the energy. So fundamentally, you cannot carry it. And again, car also the same thing. That's why Toyota Mirai, like Hyundai and all that, they're like, hey, dude, why the heck it's more expensive? It's not efficient. You have to keep recharging it. Tank cannot carry enough of it. And let's say you bypass that issue. How can you bypass it? Well, you can utilize a solid metal halide. Like, why can't we do that? Well, it's 10% by mass, meaning to carry 10 kilogram of hydrogen, you have to carry 100 kilogram of solid metal powder. Yeah, no, not happening on plane. Maybe 5 to 6 companies did try to do that stupidity with that. And again, then they realized they need cooling, more cooling than battery. So that's there. Now, round trip efficiency, what does that mean? That simply means to run, give you 1 unit of power into your wheels, you have to pay to around 2.5x to 3.5x. For example, this is from Britain. They're smoking, like, what if we did hydrogen train? They did the whole math and research and all that. And be mindful, same thing is available in Germany also, if you can read German. I do not read German, so I'm using the UK data point. And again, same data point is available in every encyclopedia. So 2.9 units of energy you have to take from the grid. Then you have to waste 30% of it when you are electrolyzing. Again, thermodynamic penalty. You cannot bypass it. Oh, better technology and no. Thermodynamics. No. The only thing we are improving is basically the cost and longevity of these things, not the thermodynamic law. So you throw away 70% energy, then you throw away some amount of more when you have to compress it. And again, they remove the transportation stage, but okay. And then you send it to your fuel cell. And that fuel cell will throw away the remainder 40%. Because again, fuel cell is a bit more inefficient compared to the electrolysis part. And then again, your current converter, basically that DC coming to and then converted to AC, and then you drive your motor for 1 unit. So to give 1 unit of traction power, you need a 2.9, almost 3. And again, I'm being way too optimistic, way too almost lol when you are talking like 2.5x efficiency. Yeah, that's not happening. You have to pay 3 or 3.5. And that simply means your grid. It does not matter where it's coming from. You have to pay for that. You have to pay. At that point, it will cost almost same as petrol and diesel at current prices, 2025 prices. And another aspect is why hydrogen was so expensive when Toyota built it. Well, because while you can troll the company, you can troll the government by subsidies and all that, you have to pay 3x more in terms of energy. Your traction motor, how much energy it needs, you have to pay 3 times more. Okay, let's say you pay that. Then you have to pay for transportation. It's not an electrical system where it's just like, okay, it's a cable and wire and once done. No, you have to keep paying for transportation. Okay. And then you have to pay for water. Somehow every design, I'm like, calculation is like, where is the water coming from? And again, once you start to do for every truck and all that, then you will realize that oxygen is this huge, hydrogen is this huge in water, like tiny, tiny balls in hydrogen. What does that mean? That simply means, if I had, let's say, 1 liter of water, like this puppy, almost only this much would be hydrogen, this much would be oxygen by mass. Like, I think, correct me if I'm wrong, I think it's 88% by mass. So you have to drink water like there is no tomorrow, have too much overproduction of oxygen, and then have tiny amount of hydrogen. And again, you have to pay for it. So that's why hydrogen is not a new technology that is coming from the future. It's an abandoned technology from 1930. We've been there, done that, learned it, forgotten about it. People became stupid. People did not go to school. They did not understand the difference between kilograms and liter, did not understand that you have to pay for it. And then subsidies can create brain damage, short-term brain damage. And then people are like, oh, Germany built hydrogen train. They forgot to pay attention to the fact that they built it in 2020, abandoned it in 2022 because they had to pay for it. And then like, wait a minute, why it's costing me so much more? You have to pay for it. You have to pay for transportation, you have to pay for the water, and you have to pay for the cost. I'm not even talking about the capital cost, which is also ludicrously high. So that's why you cannot have something that is poor round trip efficiency. If it was 100% round trip, again, let's just say 90%, it would be more than good enough. It's not. These two steps are fundamentally draining majority of your energy. Basically, 2/3 would be thrown away. So what does this mean? Well, we have to understand wisdom here, because energy can be cheap and abundant, and that's what is fueling our current brain damage of hydrogen. Because solar and wind is giving us abundant and cheap power. That's cool, awesome. Somehow people forgot cheap and abundant does not mean free. You still have to pay for it. It's not free, and wasting it is harmful and expensive, because people are like, oh, battery has so much emission and all that. How the heck you are getting electricity? Either by burning coal, which again brings you back to the same point, or hyper stupid burning methane, which again might as well just use methane as CNG, it would be far more efficient, or building gigatons of these puppies, solar panels and wind farms. And again, instead of just using one unit, you have to build, like, let's just say 1.5 unit that you will need for battery, with converting worst case scenario, 1.5x of what you need, you are doing 3.5x. So it's the same thing. Out of sight, out of mind. It's not better for the planet. It's brain damaging the planet. And again, hurting the environment, because again, super giant amount of this, super giant amount of transmission, super giant amount of infrastructure, super giant amount of grid energy storage, all of that has to be created. So it's very expensive. And on top of that, the running cost will bankrupt you. And that's what has been happening from 1930. Every time we built it, the outcome was the same. It's not efficient enough. Even if you're willing to deal with all other problems. Some car company did came very close to actually having a useful product. They had like a water cooling line going into your powder bed of metal halide powders. And again, on principle, it could work. And again, they were this close. It's just like by the time they accounted for the cost, it was like Lamborghini for basically sedan. Lamborghini-like cost, sedan-like performance. So that's why it did not work. The running cost will bankrupt you. And again, over time, efficiency becomes far more important. Think in this way. Let's say you bought a vehicle today, and whatever the fuel price is, let's say in India, fuel price is 100 rupees per liter. Do not focus on units, just focus on 100 liter. It's 100 for one. And again, I am damn sure I can buy a car today. I'm damn sure I'm going to use it for 10 years to maybe 15 years. And I can guarantee you, 10 years from now, the fuel will be far more expensive. At that point in time, if I bought a cheap car today that was like, poor mileage, it will hurt exponentially more. It's like compounding interest to my suffering. So for that reason, efficiency becomes far higher priority as time goes on. And again, Germany learned that the hard way. It's like, hey, we built the hydrogen brain damage. It's like, oh, we have to pay it. Oh, we have to keep paying it. Oh, we have to keep paying for year over year. Then it's like, yeah, no. So that's the whole thing. It becomes far more valuable. And as inflation goes up. Now, another aspect is for everyone who is focused on this sort of system, do you want people to live in this planet, or do you want to poof themselves? If you want them to poof themselves, go with hydrogen. Or if you want to make sure that planet lives healthy, understand this graph. No matter which country you look into, no matter which timeline you look into, energy cost is directly proportional to everything. So electricity is cheaper, petrol is cheaper, diesel is cheaper, everything else is cheaper. Food, water, everything. Electricity price goes up, petrol prices goes up, or whatever have you, the prices of every goods that we consume, food, water, air, everything goes up. And again, if you're wasting electricity for making hydrogen, electricity price will go up. And again, you are back to the square one. You are causing more unbearable inflation. And right now, world is almost broken. So adding more inflation, not a good thing to do. So please read history. So understand, if we do not use wisdom right now, you're gonna pay the price. I'm done with this world. So this was my presentation on basically round trip efficiency. Why does that matter? Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.